Where did the moon come from? It's a question that's puzzled scientists for centuries. Look at the other inner planets. Mercury, Venus, Mars, they either have no moons at all or just tiny ones. Take Phobos, Mars's largest moon. It's only about 20 kilometers across, so small it can't even pull itself into a sphere. Literally looks like a giant space potato, but Earth's moon. It's massive by comparison, 3,500 kilometers in diameter, roughly a quarter the size of Earth itself. For such a huge satellite, its origin story has remained surprisingly mysterious. For most of the last century, scientists debated three main theories about how the moon formed. First up, the fission theory. This wild idea suggested Earth was spinning so fast that it literally tore itself apart, and the moon formed from the chunks that got flung into space. Then there was the capture theory. Maybe the moon wasn't born here at all. Maybe it was just wandering through space, passed too close to Earth, and got caught by our gravity. The third theory, co-accretion, proposed that Earth and the moon were basically twins, born together from the same swirling disk of material that formed the solar system. But today, most scientists favor a much more dramatic explanation, the giant impact hypothesis. Picture this. About 4.5 billion years ago, a Mars-sized planet called Theia smashed into the early Earth. The collision was catastrophic. Massive amounts of debris were blasted into orbit, and over millions of years, that debris slowly clumped together to form the moon. Sounds like the perfect explanation, right? Well, not quite. When scientists analyzed moon rocks brought back by the Apollo astronauts, they discovered something weird. The moon's chemical signature is almost identical to Earth's. Same isotopes, same composition. But here's the problem. Theia came from a different part of the solar system. Should have a totally different chemical makeup. So why do the moon and Earth look like they're made of the same stuff? That's been one of the biggest mysteries challenging the giant impact theory. Just last month, a new paper in the Astrophysical Journal Letters offered a fresh take on what might have happened. Researchers ran hundreds of computer simulations, diving way deeper into the collision details than previous models. What they found was fascinating. After the impact, the debris might not have formed a ring around Earth. Instead, it split into two separate clumps, one closer to Earth, one farther away. The distant clump was beyond Earth's Roche limit, the point where gravity would tear it apart, so it stayed intact and eventually became the moon. The closer clump, Earth's gravity shredded it, and it rained back down onto our planet. Since most of the moon's material came from Earth itself in this scenario, that could finally explain why they have the same chemical fingerprint. But there's another piece of this puzzle we need to talk about, the moon's far side. You know how the moon is tidally locked, always showing us the same face? We call that the near side. The far side is the one we never see from Earth. Before we sent probes up there, astronomers assumed both sides would look pretty similar. Boy, were they wrong. When the first images came back, they were stunned. While the near side has those familiar dark plains we call Maria, ancient lava flows filling giant impact basins, the far side is completely different. It's rough, mountainous, covered in highlands. The crust there is way thicker too, about 50 kilometers compared to just 30 on the near side. Even the chemistry is different. The moon literally has two faces, and that has to tell us something about how it formed. So scientists came up with some creative theories to explain this. One idea is the near-side heating hypothesis. After the giant impact, both Earth and the moon were molten. Earth was basically a gigantic ball of lava radiating intense heat. The moon's near side, facing this cosmic furnace, stayed hot longer and had more volcanic activity, creating those smooth lava plains. The far side turned away from Earth, cooled faster, and developed a thicker crust. Now you might be thinking, wait, would Earth really be hot enough to heat the moon from that far away? Fair point at today's distance of 384,000 kilometers. Probably not. But here's the thing. The moon is slowly drifting away from Earth at about 3.84 centimeters per year. Wind the clock back 4.5 billion years, and the moon was way closer, maybe just 1 or 2 Earth diameters away. At that distance, Earth's heat would have been intense enough to make a real difference. There is a catch, though. If they were really that close, orbital mechanics suggest the moon should have spiraled inward and crashed back into Earth, not drifted away. So this theory has some holes. Another idea proposes a second impact. After Theia crashed into Earth and the moon formed, maybe a smaller body slammed into the still molten moon. The debris splattered across to the far side, piling up to create those highlands. The near side, where the impact hit, got melted again, which changed its chemistry. But this theory has problems too. If the impact happened while the moon was still molten, Those impact craters we see on the near side today should have been erased, not preserved. Then there's the dual satellite hypothesis. What if the Theia collision created not one moon, but two? These sibling moons orbited at different speeds, and eventually the smaller one caught up and gently collided with the larger one, a cosmic rear-ending. The debris from the smaller moon splattered onto one side of the larger moon, creating the Highlands. The two moons merged, and boom, you've got a two-faced moon. So which theory is right? Honestly, we don't know yet. We need more evidence. But the good news is, we're getting it. In 2020, China's Chang'e 5 mission brought back 1.73 kilograms of fresh lunar samples, the first new moon rocks in over 40 years. Analysis of these samples led to 3 papers in Nature that completely upended our timeline of lunar volcanism, pushing it forward by 2 billion years. Scientists found evidence that the moon stayed volcanically active way longer than anyone thought possible for such a small body. But that raised a new question. How did the moon's interior stay hot for so long? Chinese researchers solved that mystery by finding unusually high levels of calcium and titanium in the basalt samples. These elements lowered the melting point of the lunar mantle, keeping it molten longer. Meanwhile, NASA is also getting back in the game, finally reopening Apollo samples that have been sealed in storage for 50 years. New technology, new insights. But here's the thing. All the samples we have, whether from Apollo or Chang'e 5, come from the near side. To really crack the mystery of the moon's origin, we need rocks from the far side. And that's exactly what China is working on. Chang'e 4 already made history of the first spacecraft to soft land on the lunar far side. Next up is Chang'e 6, which aims to bring back the first ever far side samples. When those rocks make it to Earth, we'll finally be able to compare both faces of the moon directly. And who knows, maybe that's when we'll finally solve the mystery of where our moon really came from.